we did a mechanism, right? So A can be hydrolyzed, right? We did one of the two mechanisms. B can be hydrolyzed. That's where we did hydrolysis of ester in base, and we started with that. That's why I felt like we did base hydrolysis of this, because we didn't do the acid and then the base, we just did base of this and then acid of that. That's what I felt like. But it's going to be roughly the same. So we can hydrolyze both of these, right? So are they both going to hydrolyze at the same rate, or will one of them react faster? Let's see. We're going to vote same. What do you think? Okay. Who thinks that A is going to go faster? Who thinks that B will react faster? So, wildly enough, B is going to go faster than A, and we can go back to this and go, oh, you know what? That actually kind of makes sense, because A was an amide, right? Hydrolysis of an amide, so amide is further down the scale, less reactive than an ester. So esters are more reactive. They're going to hydrolyze faster than amides will. That little table is very nice. Okay. Acid halides and alcohols. So if you have an acid halide and you react it with an alcohol, you're going to get an ester. Very similar to when we had an acid halide and we reacted it with water. So OH, and we got a carboxylic acid. This time it's OR, and we get an ester. No catalyst necessary, because if you blink at an acid chloride, or, well, not just chloride, but they're usually acid chlorides, if you blink at an acid halide wrong, it is going to react, right? So if you give it no water to react with, then you're not going to ruin your chances of making an ester, right? If you have water in the alcohol that you put in, then you're going to make some ester, and you're going to make some acid, and you're going to have that in equilibrium, and then you're going to be trying to push equilibrium and separate them. Let's see. If the alcohol or ester is sensitive to acid, remember when we react acid halides, we end up with HCl, right? Which, I mean, okay, HCl isn't overly meaningful because, well, okay. Actually, it is meaningful because we usually do this without any water around, right? So we actually do have HCl, not just deprotonated, not just separated, right? So we've got a nice strong acid. If our product is going to be sensitive to acid, then we are going to put something else in there to make it so that we don't end up forming a strong acid right next to the thing that is really sensitive and gets eaten up by acid. So we're going to put in a tertiary amine. Tertiary amine, if the amine doesn't have any hydrogens, so like deprotonate or anything, tertiary amine, this guy is a really nice base. And is it really a nucleophile? I mean, not really, because sure, you could take that lone pair and attack, but then what are you going to do? You can't get the charge off of the nitrogen, right? Because this is aromatic, which we'll learn later is you don't break aromatic rings unless we're actively trying to. Those things are very nice and stable. So basically, there's nothing really to like mess with here chemistry-wise. So this guy is not really a nucleophile, but it is a pretty darn good base. So we'll put in a pyridine, triethylamine, something like that, to convert to the hydrochloride salt instead of a strong acid. well, and also because tertiary means like triethylamine, that's just 3 ethyl groups on an amine. That's sterically hindered, right? So like, also not going to be a very good nucleophile just because it's sterically hindered. So it can be a nucleophile to hydrogen because those are tiny, but that's also called a base. So, does that make sense? Okay. So, yeah, your amine is hydrochloride salt, and we've got this sulfonic acid esters. So this is tosyl chloride. And did first semester, did you talk about these sulfonic acid? Did you talk about tosyl? Okay.
For about 15 minutes.
For about 15 minutes? Okay. Not a ton, but like it exists in our minds. Cool. I'm not going to be afraid of using it, but I will draw it for you if we make you use it. Yeah? Sound good? Okay. So basically, the only reason we use tosyl and like TS, this looks like an element name, right? It's like in the style of an element name, but this isn't, specifically TS is nowhere on the periodic table, which is why we're allowed to like make a shorthand like this. This is how inorganic chemists name everything. They make a bunch of shorthand names for whatever section of organic things they have or whatever ligands they have, and they just sort of give them nicknames, shrink it down, and sort of name stuff that way. It's funny. But anyway, when we use tosyl, we're looking at really good leaving group, right? That's what we see when we see that. So, are we gonna, hold on. Do I have a hidden slide in here? I don't have a hidden slide. Okay, cool. Oh, no, I have, we did acid chloride with an H3, right? Yeah. Where are we? No, we're here. Okay, no, we're getting there just later. Sorry, I just didn't put cues in my notes, so when we start going past several slides that have the title of the mechanism I'm looking for, I start wondering where I hit it. Tosylate and mesylate are 2 things that exist. Tosylate is TS, mesylate is, I don't actually remember, but methane sulfonate, that's just this guy. So chloride, it's this, and that's just a methyl group. So mesyl and tosyl, I think it's MS for mesyl and mesylate. So I guess tosylate and mesylate are without this. Right? Oh, no. Toluene sulfonyl chloride. Here we go. It includes the oxygen. There we go. It includes the oxygen when it's a good leaving group. So we can start with this, but basically we end up with an oxygen that was already there. We get rid of chloride because chloride is a really good leaving group, but it's going to take its electrons with it. So we're just going to have this guy. This guy is going to end up attached to the oxygen, and then once it does, it becomes actual tosylate or mesylate, and it takes that oxygen with it and is a very good leaving group. So that's what those guys do. Yeah, MSCl, it's up there. There's way too many words on these slides. I hate it. So really the only sulfonyl chlorides we'll ever play with, and I'm not going to make you do mechanisms with them because, nah. Acid anhydrides with alcohols. You get acid anhydrides and alcohols were still there. Okay, so you get ester and 1 mole of ester, 1 mole of carboxylic acid. Oh no, wait, this is acid halides with alcohol, right? I thought I had an acid halide. No, I don't. Okay. This is why I have these in front of me, so I don't just start drawing every mechanism and then take 5 and turn it into 20. But it's gonna look really similar to other things we've seen, right? We've already seen hydrolysis of an acid halide, right? So exact same thing, except your OH is gonna be an OR the whole time, because it was an alcohol instead. So acid anhydrides and alcohols, they start out with 2 carbonyl groups, and remember, acid anhydrides are basically, we call it anhydride because it's 2 carboxylic acids, and then water was taken out, so we took out the OH of one, and we took out the H plus of the other, and smashed them together. So we've got 2 carbonyl groups, and we're gonna have to do something with them. So, excuse me, what's gonna happen is, if you take alcohol and put it in with an acid anhydride, you can catalyze this with an acid or a tertiary amine. So these guys are, they'll react with water without like help. Acid anhydrides will. If you want them to react with alcohols, I don't know why, but they need to be catalyzed with an acid or a tertiary amine, so a tertiary amine base, ester base. So if you put in ethanol, basically one of these guys, instead of becoming a carboxylic acid, one of them will become an ester with OR, R being whatever your alcohol is, and then the other one will just become the acid, the carboxylic acid. Yes? So breaking an acid anhydride in half, but one of them gets to have, well, if you specifically give 1 mole of ester and 1 mole of carboxylic acid, you're gonna get 1 ester and 1 acid, right? So, yeah. Let's see. Aspirin is synthesized by treating salicylic acid with acetic anhydride. And you guys might have done a lab on this, or might be doing a lab on this. No, you should not lick the aspirin afterwards, even if you have a headache, because one, no food or drink in lab. We don't sample the lab stuff. Like that's a hard and fast rule. And 2, guys, other Organic 1 and Organic 2 students used your glassware, and also all of those chemicals are kept in a stockroom next to all of the other much scarier chemicals, right? Because all the scary chemicals are kept in the stockroom altogether. You don't know what these things are stored next to. And again, other undergrad students used your glassware. So like, I mean, I wouldn't trust glassware that had ever been used for any sort of chemical ever by anyone, right? I don't care who tells me that they cleaned it enough that it's now food safe, or like how many PhDs they have. I'm not trusting that, right? So think about how well you wash things, and then remember, a bunch of other people in this class were rushing to finish a lab, and yeah, don't lick the aspirin. Deal? But you can do salicylic acid with acetic anhydride, and you can make aspirin. Whee! Don't take that if you're a kid. Esters and amides with alcohol. So you can take an ester or an amide with an alcohol, and you can do transesterification. It makes a whole lot of sense with an ester. One ester to a different ester. Transesterification, we're taking one ester and switching it out for a different ester group. But we still call it transesterification. Okay, no, we don't. Yeah, okay. Transesterification is making an ester into a different kind of ester. Amides, they're least reactive, right? When we had that table, amides are at nearly the very bottom. So amides are way less reactive. For transesterification, if we start with an ester, we just have to use an acid catalyst, but we are gonna get it at equilibrium, right? So then we're going to wanna push equilibrium with like a ton of alcohol to try and get as little as possible of the ester that we don't want, so that when we run the column, it's nice and separate-y and not all over the place. Amides are the least reactive of functional derivatives. They don't react with alcohols, like at all. Why are you going to tell me reaction of esters and amides with alcohols if oh, okay, because we're going to talk about turning that into an ester. So, amides, you put that in with an alcohol, it doesn't do anything. It doesn't care, right? Amide is almost the lowest on the tier. It doesn't do shit. Esters, you can do transesterification, but you're going to be at equilibrium, so push your equilibrium. Let's see. We can react ammonia and amines with acid halides. So, we can have an acid halide and react it with a primary or secondary, with ammonia, or a primary or secondary amine to form an amide. So 2 moles of ammonia or amine are required per mole of acid halide. For every mole of this, you're going to need 2 moles of that. And that's because this is going to act as both the substituent, because when you have the product, it kind of looks like we only need a 1-to-1 mole ratio, right? But this guy is going to act as both the substituent and the base. And this is not base catalyzed, it's base driven. So you need 1 mole of base and 1 mole of, well, your nitrogen substituent to make the reaction go. So you end up needing 2 moles of your ammonia or amine to form an amide out of an acid halide. All right. Okay. We're just going to talk about some more. We've got only a couple minutes left, not enough to do that mechanism. I will decide later if we go over the mechanism or not. Most of these mechanisms are really similar. So they all look very similar. Try them out at home. Try that at home for fun. Like, see if you can do the mechanism without looking at this mechanism in your notes, but try and look at like the ester mechanism in your notes, and then try and figure out this. Yeah? Make sense? Or like hydrolysis of an acid halide, look at that mechanism and see if you can work this out, and then check it. Come hang out with me in office hours. Okay. Acid anhydrides react with, this is the same thing, but with a different picture. It's literally the same thing, right? Is there anything different between these? No, 2 moles of ammonia or amine are required. It is the same thing, but a different.
It's not a halogen.
Oh, thank you. See, these all just like, they all are just carboxylic acid derivatives to me. So acid halides and acid anhydrides just, I don't know, they blend together. So you can do this with an acid halide and you get an amide, but you need 2 moles of this because one of them is base. Over here, you're gonna need 2 moles again. And what you're gonna form is, you're gonna need, same thing. One is going to be your substituent, and one is going to be a base to neutralize the acid that you form. It's just that instead of forming HCl and neutralizing that, you're gonna form, well, the other half of the acetic anhydride into an acetic acid, but neutralize it. Yes? Okay, so we can go over, they show the mechanism of this, not the mechanism of this. They'll be very similar. Okay, we're gonna get through talk about